Okay, I guess we can start. Okay. So it's a great pleasure to welcome Olga Postnova to give the first seminar in the new campus. Okay, so Olga comes from the Euler International Mathematical Institute, and in today's talk, we will talk about Skew Howe duality and the limit shapes of Venn diagram for classical videos. Welcome.
Thank you. I'm very honored to be invited to your joint seminar. It has been about a week that I have been here, and I have also given one seminar yesterday. All that I can say is I'm very amazed with this new campus and with the scientific community that was created here. So thank you again for inviting me. Today I'm going to talk about the joint work that we have been doing with Anton Nazarov, Pavel Nikitin, and Travis Grimshaw on the limit shapes of Young diagrams, and how this problem is in fact connected with the Skew Howe duality. So maybe I would right now give some introduction to the problem. So actually the problem of limit shapes of Young diagrams goes back to the Ulam's problem on the length of the longest increasing subsequence. And actually, it was firstly the limit shape for Young diagrams was studied by Schur, lozenge, in 1980s. So after we applied this in fact this problem is actually connected with the RSK algorithm, but I will be telling about this later. Also the problem of limit shapes and the idea of the tensor product decomposition was later studied by different authors. One of them was Kirov and Young. Maybe I can show you the slides. But actually, this is one part that was studied, and then there is this Skew Howe duality, which I have introduced as in the name of my talk. And how what does this have to do? So basically, that is the purpose of my talk is to explain how this fact from the representation theory will help us to derive the limit shapes for various problems using for various algorithms. So basically, that is the short advertisement of what we have been doing. Okay, let's see if does that work. Now the presentation does work. No. Yeah, maybe I will just say. Yeah. Okay. So as I have announced earlier, so firstly, the one thing that everybody knows is the Schur duality. So if we consider such a space, we will have the unity actions of symmetry energy. And actually, we can consider this as a bimodule. And here we will sum up of the partitions of size A with the number of rows that is. So in fact, we can introduce the measure, and that is what Kirov did in 1986. he used the Schur duality to construct a measure on Young diagram of size. Size. So I can use this word. Yeah. Okay. So here it is possible to derive the explicit formula that is what Karen did, because the dimensions of the GLN module is known, and also the dimension of the module of the symmetry group is known. And so the following expression for the measure was used by Karen. So yeah, okay. So now using the Schur duality. Now, if we try to ask the asymptotic questions, so there were various studies in the various regimes that the asymptotics have been studied. So, what we do, we consider so Longitude shape. That is what I was telling about in the beginning. It is the regime when the n and k goes to infinity, and the ratio of k and n goes to the cost. Now we have this the famous curve shape of the Young diagrams. And also there were some studies in 2000, the year 2000 by Young, where he had the deformation of the shape by also by this regime where k over n squared goes to constant. But that was studied long ago. So this is just some introduction of the scope of the problems that the asymptotic representation theory, well, in St. Petersburg also have dealt with. Oh no, it's yeah. Okay, yeah, and the important thing to note is that the Schur duality is actually, we must note that we can see the combinatorial interpretation. So when we consider this space, it can also be considered as a tensor power of the GLN module lambda 1. So okay, this is the fundamental module which is depicted by the box diagram. And inside this module we have the basis. So the basis will correspond to the filling of this diagram like that. So this is the standard mod. So then we can say that we can consider this decomposition. So then using the usual RSK correspondence, we can have the pair of a standard Young tableau and a semi-standard Young tableau. So in that way, we can produce the diagram. So and the question for other serious algebras basically remains. So now this question is more complicated actually than it may appear. Firstly, because, well, yeah, okay. Because there are some other dualities besides Schur duality. There is the just the duality. So the first is Schur duality. I have talked about this now. The duality. So when we consider the Howe duality, the usual Howe duality that probably you might be aware of. Sometimes it's called the GLK. Howe duality. This is the more or less known name for this. So that's where you consider the symmetric algebra, and then besides the fact that this space is infinite-dimensional in a more or less sense, you can make this decomposition. But now if you will try to study certain asymptotics, then it makes sense to make some restrictions on the diagrams. So, and the asymptotical problems related to actually the Howe duality have been widely studied. Well, first thing, how can we deal with those diagrams is that we can consider the diagrams of size M, or we can consider diagrams which are contained in the rectangle that was studied by Schur, and also it's related to the Arctic circle of lozenge size and Han ensemble. Later, I will tell how our problem is related to what tilings and to what ensembles. So this relation is actually well studied. And also, there is another approach using an approach by people that regards the Schur measure on partitions. So, because we can consider the characters and the corresponding Cauchy identities. So basically, here is a very, very short historical facts. How the idea of the asymptotic study of the Howe duality has been treated previously. But there is also the duality that we are going to talk about now is the Skew Howe duality. Okay. Why have we come to such a problem? So at first, we have been studying the tensor product decompositions. And we have been looking for cases where, so the tensor product decompositions of certain modules, then we can decompose it as sum of the lambda and lambda depicting of the difference on the tensor power. And so we have been studying such decompositions, and we were trying to understand in what cases this formula has a nice shape. So there are various ways to get this multiplicity. If you consider such tensor products for simple Lie algebras, they are known, but not well. In a general case, these multiplicities are very complicated, and it's hard to consider any asymptotics using those formulas for multiplicity, because if you consider the asymptotics of the ring going to infinity, it may be difficult and somewhat troublesome. But in our research, we have discovered certain cases where these multiplicities have nice formulas which are also vectorizable, and we thought that maybe that might have been related to certain facts, certain dualities, which appear on the representation theoretic level. So yeah, and at that point, so for example, one of those examples was we have considered the spinor model of S of n plus 1. And we have looked at its tensor powers. So actually, these multiplicities, and we have decomposed them into irreducibles. And also, these multiplicities turn out to be really nice and factorizable properties. So later, we have calculated some asymptotical results. We have found the limit shades. I will talk about that a little bit later, but the question was still remain why the formula in this case is factorizable, but for example, if we consider the vector module, then the formula is not factorizable. Okay. So yeah, so that was how it happens. So I want to say the experimental way that we have come up to this duality. So let me tell more about Skew Howe duality and what is it all about. So in 1989, in the article of Howe, he had shown the dual pairs of Lie groups. And later in the article of Lozenge and the module of the bimodule for these pairs of Lie groups was described explicitly. So the fact is that if we consider these pairs of Lie groups, so again we have EGL and DLT. And both of them, we have two symplectic groups and associated plus one and P. So we will have the duality regarding the certain representation, but what representation? Okay, let me say now, maybe you have already guessed if it's called the Skew Howe duality. It has to do something with the Schur algebra, because we already have the usual Howe duality, which is connected to the symmetric space. But now, what about exterior algebra? Yes, so this Skew Howe duality is exactly about this case. So if we consider the natural module of the first group, and we consider the natural module of the second group, and denote them by B and W, okay. So we can say that actually, if we consider the exterior algebra of such a space, of a tensor space, where the B is multiplied by W. So then, explicitly listed the modules, then we will have the certain multiplicity reactions of these groups. So this is one fact. This is called the GLT. So here you must know. So this is a bimodule. So exactly, you consider this exterior algebra, and you consider this space as the bimodule GLT. So here, in the first place, it is a irreducible module of GM corresponding to Young diagram lambda, and here is the lambda bar prime. So it's important to note that these we sum up the diagrams that fit inside such a box and times k. So, and how does the lambda bar prime get to the lambda? It's like this. So it's conjugated transpose diagram. So here in the small example, you can see that for GL3 we have lambda, then we have the GL4, and the lambda bar prime is actually this piece, third conjugated and transposed. So I have not written here that we sum up over the not over the diagrams, but the diagrams that inside the box, but I have explained it, so I hope there won't be any problem with that. Can we have the next slide, please? Yeah. So, and again, so I have started my talk about the tensor powers and how does the Skew Howe duality can help us. Okay, so exactly, we can consider the action of one of the groups in the pair. So we can consider a GLN module and take it to the tensor power case. So this Skew Howe duality GL and GLP, which we have established previously, could be seen just on the level of the tensor product decomposition of representation of one of the groups in a pair. So here, or what does happen here? So we take the exterior algebra of the vector representation of the GLN. Then, okay, this is a module, one GLN module. So then we take its tensor power, which is the GLN module, and then we decompose it into irreducibles with the following multiplicities. And here you can see that actually the multiplicity in the center product decomposition is the dimension of the GLP module corresponding to the diagram of lambda bar prime. And that is kind of makes some hope and gives us some hope about whether this is the case of where the multiplicities could be factorizable and easily described. So if we try to look at this Howe dualities for the other pairs of the groups, maybe that will help us to answer the question about this exact example. So why do we have the spinner tensor power of the spinner module of SO to n, which is factorizable? But we'll get to that later. So the multiplicity is factorizable. Okay, so both GL and GLP is the simplest example, and basically I will spend most of my time telling about this. But if I have some time, I will talk about this example. So can you have next slide, please? Okay. So again, now we have all the rights to use the Howe duality for the other pairs of the groups. So if and to see what formulas for the tensor power decomposition does it give us. So if we use the SP to N as P to K Skew Howe duality, we can consider again the standard modules. And in that case, they are even dimensional. So they could be described as a sum of the isotropic subspaces with respect to preserved symmetric binomial form. And here we have the statement of this Skew Howe duality. So in that case, we will have exterior algebra of the tensor products of one of those spaces times CP. So actually here, and then the Skew Howe duality state that it has that multiplicity creation. Okay, so again, we can see that here is lambda and here is lambda bar prime. Again, the diagrams are, well, they are a little bit different from GL diagrams, but actually lambda bar prime could be obtained from lambda using the same procedure. So, and again, this problem considered as the problem for tensor power decomposition of SP2N module gives us decomposition into reducibles. Again, we have the tensor power, we have the exterior algebra of this even dimensional space. We decompose it into reducible, we have the dimensions. So
again, is Skew is a shifted partition or partition?
Well, it is the partition actually. Yeah, we have certain modifications of the Young diagrams for different cases. No, it's okay. It's okay. Okay, so next. Yeah, so okay, so here is the duality actually SO2N plus 1 into K, which helps us to give the answer to our problem. It's a little bit complicated, so maybe I will need to draw something right now. If I would have, oh yeah, this is really not something that can help me, but okay. So what happens here? Again, the same procedure. The standard module is C to the 2K and the C to the 2N plus 1. So the standard module decomposes just like that into the sum of the irreducible subspaces. And again, the Skew Howe duality in its most general formulation tells us that we have these actions. So in multiplicity free actions. So here the lambda the modified Young diagrams, which basically have the first column with 1 half. So because we have to somehow describe the spinner modules. So in fact, and we also have some fillings with different, not just with the numbers from 1 to n, but from the numbers 1 bar, 2 bar, k bar, n bar. So I'm not telling you this here because it's a little combinatorial trick. But actually, again, considering it as the dimension problem, we discovered this. Okay, so now you take a look. That it kind of looks the same as our problem here, only the problem here we have the spinner module, okay, and here we have the exterior algebra of the fundamental of the standard module. So is it yeah, I can get this.
Oh.
Okay, yeah. So here we have the spinner representation. Yeah. And here we have the exterior algebra. Well, does anybody guess how this can help us with this? Because well, at first point, it doesn't look quite the same. Do you have any ideas about that? Maybe I can spend some of my time trying explaining certain example. So maybe I can make a smaller example, so not in the most general case. If it works. Okay, so if we consider the SO2 n plus 1 case, we can see a short example in the representation in the weight space. We consider the weight space of the Bernoulli values. So okay, we can say that here this the alpha 1, alpha 2, and here is the weight diagram. Diagram of W. Okay, so it's 5-dimensional. So it's 5. So this representation is 5-dimensional. Okay. Then what about spinor representation? Well, spinor representation, we know that it's 4-dimensional. Okay. So what does it have in common? Well, the question is that in fact you can consider a tensor square of the spinor representation, and the tensor square will give us exactly some part of the exterior algebra. Okay, so if we consider the tensor square, how do we in the level of the weight diagrams of representation, how can we construct a square, tensor square? So basically, we will construct the diagram, which is larger in the point. Let me just okay. I should erase everything which is out of ordinary. So that was the previous state implementation. Then we make a tensor square. So how do we do? We start this diagram from the very point where it begins. So we can have something like this. Okay. So here we also have multiplicities too, right? And here we'll have multiplicities 4, I guess. Okay. Okay. So, and if we consider the exterior algebra of W on the level of the weight diagrams, it could be seen that it exactly corresponds to spinor representations squared. Well, I make 2, so 2 copies of that. So that is so this is just one of the components, okay? But you can have, so this is, you can have lambda 0 W plus lambda 1 W. Okay, so and actually you can make this a short exercise because I wonder maybe I'll be spending too much time on that. So that this the exterior algebra of this representation exactly correspond to the two times square of this spin representation. So and that's why this Skew Howe duality can actually help us to solve this question. So there is not actually a duality for the spin representation, but there is a duality for the exterior algebra of the standard representation. And again, due to this relation, that will help us to get the answer to this problem. So can I have the next slide, please? Yeah. So that was that's in the most general case what I have been talking about. Exactly. So this spinor representation is the last fundamental representation. So, and we have this as in the business of the whole exterior algebra of the standard representation to the two types of square. So again, we try to right now there is some additional knowledge about that the P group actually is a two-point cover of O2K, and also that we can use SO2K dimensions to obtain P2K dimensions. Because on the language of how Skew Howe duality, we have SO2n plus 1 P2K duality. So but we actually would like to have those because this is kind of knowledgeable. So, and in the very last very last step, we obtain this formula for the tensor product multiplicities. So again, Skew Howe duality helps us also in this question. And yeah, so I won't be maybe spending too much time on the last pair of the groups. So it's SO2 and O2K. Again, we can consider the isotropic spaces, but in fact, by the very end of this procedure, it's important to, okay, so I didn't put it as a square, so for some reason, it depends as a part, for some reason, it had disappeared. Okay, maybe, okay. So actually, what's important to understand that here we can decompose a tensor power of the sum of two fundamental representations. So because the exterior algebra that in the very end that we are looking to, the exterior algebra of the standard representation could be decomposed into sum of even and odd powers, and these two modules are exactly the last fundamental module of SO2 and the one before that. So this is the sum that we should have the tensor power, then it could be decomposed into reducible. Well, if I had time, I could have shown you the way diagrams there, 3-dimensional for SO6. They're kind of nice, but probably I wonder if this is more suitable for now. But again, this is there is some nice examples that you can actually have by using this type of grid. Okay, so here basically I have listed now all the probabilities, Skew Howe yeah, here on the slide. So what is the summary of first part of the talk? That the Skew Howe duality can help us to obtain the multiplicities in the tensor power of the certain modules. So for GLN, this is the exterior algebra of nature representation. For SO2n plus 1, it is the spinor fundamental representation. For SE2n, it is the exterior algebra of nature representation. And for SO2n, it is the sum of the spinor representation. So this is actually the fundamental the facts that right now we have the answer. So if we consider these tensor powers, then we have the answer to the tensor power decomposition problem with the formulas which are factorizable, and these formulas could be explored with the asymptotic instruments. So then you can state a problem of how can we look for limit shapes of Young diagrams. Maybe you look for central limits theories. So when we have the formulas, now this question actually, the answer to this question can actually become real. But to do the asymptotic analysis, we actually have to do some a little bit more extra work because you know, we have in the parts of the formula we have diagram lambda, but the multiplicities are expressed via the lambda bar prime. So what can we do? So now we should be doing some technical work. So how can we relate the parameters of lambda bar prime to the parameters of lambda? Okay. Okay, but that's for a little bit later. Right now, I wanted to say that there is such as an RSK algorithm corresponds to the Schur duality. Just in the very same manner, we have the so-called dual RSK which can help us to construct random Young diagrams corresponding to the Skew Howe duality. So how does it work? So firstly, we can say that the basis in this space, so we consider the exterior algebra of this space. So the basis of this space is the following. And the basis of the exterior algebra is actually the exterior products of these vectors. Okay. So now we can, I will show you how can we take a simple example. And actually this could be related to the matrix of random matrix of zeros and one. I don't think we can maybe have this. So here is the vector from the exterior power, and you can see that, okay, we put the numbers 1 at the positions where we have non-zero parts in this basis vector. So then here we can make a correspondence with this type of sequences. And here again, so they're corresponding to this n times k matrix from 0. So what is such a sequence? Now we can introduce a dual RSK algorithm, which how does it work? It works like we bound the boxes with the equal ends and down. So at first we have 1 here, then we stick up the 2 and we stick up the 3. But when now we have this number 2 appearing, okay, so this number 2 it goes exactly right here, and we push this to be yellow down. Okay, then now 4, 6 here, and this is not a very interesting example, though. But yeah, the interesting is that 1 is actually goes here. So, well, that is a very simple point. It's a simple example, but one should know that. So we can use this algorithm, and also this algorithm is for GL and GLK. You must understand, because for other algorithms we have more interesting algorithms. Maybe I can just name them. Maybe if I have time, I will talk about them. They are more sophisticated. So by the end of the application of the dual RSK algorithm, we have the pair of 2 semi-standards Young tableau, okay, P and Q. So in that sense, we can now relate. So and they have the same shape. So we can now relate the diagram of a certain shape to what we had in the beginning. They can okay, then right now there is some technical part which I will try to go real quickly. Because what I wonder is, well, at the very end, we need a formula for dimensions, okay? But how can we calculate those dimensions? Well, one of the ways that we use is actually the algebra lemma, and algebra has can deal with paths. So at that point, we have to make certain correspondence between the Young diagram that we have obtained using our method with certain paths. And there are actually 2 ways we can do that. One of the method is the row bijection. So here you can see this on the example. This is the lambda bar parameter diagram, because well, I really want to deal with this diagram actually. So in the row bijection, you can you should construct a path which correspond to the row. So here you can see the path here corresponding to the first row. Is something to the right. So we have 1, 2, 3, 4, 5, 6 paths, and actually we have 6 rows. So the last row is empty. It's simple to understand. But we have this example equal to 6, and it is not there. So what do? We make a correspondence for each row to the lattice path with certain steps. We say that the starting points are the following, and the endpoints are the following. And the topmost row is the corresponds with the rightmost path. Well, this is quite technical thing. All of you can do this using this recipe. Just sometimes I could just say use row bijection. So probably I won't be dealing much here. Actually, here's the recipe. All of you can apply it. Do this way. We can have a slide. And also there is the so-called column bijection. So now another way to make the paths corresponding to Young diagrams is that you can the young tableau is that you can read by columns. So now the first column corresponds to this path, which is the rightmost path, and there is a certain recipe to do that. So now the steps are -1, 1, and 1, 1, and we have a certain starting and ending points. So to this, the tableau is read from top to bottom and from left to right. And with this reduction, we have the following subset of the paths on L lattice. So can I, okay. So, but then there was one combinatorial correspondence for GL and GLP. Another one is that we can use actually the GT patterns or the lozenge tilings. So right now we have understood that the dimension of the module corresponding to lambda bar prime equal to the number of semi-symmetry chunks of the shape lambda bar prime filled with numbers from 1 to 2. Okay, and exactly everybody knows that we can count this by counting the corresponding GT patterns. Well, if we construct the GPT pattern corresponding to this diagram, it is this triangular array, which has the recipe of doing that. But there is an easy way to memorize how the GT pattern can be constructed from the tableau. Is that on the first row we have the row lengths. Then we have the row lengths of the young tableau if we exclude the bigger number. So here we exclude 6. Then on the third row, we directly list the row lengths if we exclude the 2 bigger number, 5 and 6. So here you can see that this array can be easily constructed from here. So 5, 2, 3, 1, 0 is the row length. And then if we cancel the 6, right? And here, so we have this second row 5, 3, 2, 2, 0. So and another way. So it's one of the possible combinatorial construction that could be related to that diagram. But actually, we will use another way. Another combinatorial tool is the lozenge tilings. Can I have one second? Yeah. Well. The lozenge is the well-known combinatorial construction, and it has been also widely used for the regular Schur, while the duality and for regular Howe duality. But here we have thought of a way how could we some tilings hexagon or maybe not hexagon. So which types of tilings actually correspond to our young. So right now we have this patterns, and we can say that the numbers on the first row will correspond to the positions of the blue tile if we count from the bottom. So here these numbers are actually the position. Well, here there is nothing new, only that it somehow stops in the middle. Because you can understand that here n and k should not be equal right now, and you can see that this part actually has 6 kind of steps, and here there are five vertical possibilities to start the paths. So, and well, if we try to close it, that's would be kind of the shape will not be symmetry. But that's not such a big problem. We have found a way how to deal with that. Also, the important note that I would say is that here, if you might remember that this shapes, this blue paths look somewhat familiar. Yes, and in fact, those are the paths that we have 2 slides ago. Those are the column readings, which we have found for our diagram. So, and one way is just to read the columns of the column reading. Then another way is just to draw the GT patterns, to draw this tiling, and then to assign certain path steps to this tiling. So it's 1-to-1 correspondence. So yeah. Also, So basically, and if we, you must understand, so if we here write down the position of the tiles, then we have basically defined everything. So we have defined the young window, we have defined the corresponding G pattern. So there is no other way of filling. So they this tile exactly define our field. So can I have the next? Yeah. But for the purpose of the later work, it's valuable to define the positions of the endpoints, because right now we will be dealing with the positions of the endpoints in our resulting formulas. So, and the positions of endpoints are basically, they could be defined via the row lengths of the diagram lambda. So here you must know that we have started from lambda bar prime. Then we have obtained lambda. So lambda is this table, and the A's could also be used using the G-dependent. So in the very end, now we have a certain way you have to deal with lambda bar prime and how they are related. So can I have the next slide, please? Yes, and the next slide. Yeah, because this is, yeah, okay. So, and that is what we have come up to this point. So if you see, our hexagon is kind of not very symmetric. Yes, because here we have, and six steps, and here we have five vertical positions and so this is kind of like a problem, because we should somehow connect them, and actually one doesn't have a special material construction of how to describe that, because this is kind of a technical construction. And here in the middle we have the positions of this triangle that actually correspond to the shape of the young diagram. Okay, and here we can say like we have paths which correspond to the whole region, and here we have paths that correspond to the whole region of the lambda, but they are kind of badly connected. You can somehow issue a way of how you can connect them, but that's not very convenient. And also appearance of these triangles is not very convenient. So, well, regarding one thing in this combinatorial construction, we can say that it is in one-to-one correspondence with the tilings of the Aztec diamond, where you can have tiles with three possible dominoes on this part, which is it has the highest K, and then the tiling of another type of three possible dominoes on this part. So exactly, and you can see that those dark gray triangles will correspond to these horizontal steps and to the green dominoes. So so here basically now we can reformulate our statement as how do we calculate these tilings of such an Aztec diamond. The diamond has three possible dominoes in one part and three possible in another. And here we have a simulation provided by our co-author Vitia, where it's kind of small. Well, I actually have included this in the slide. So basically, it shows like if you consider a simulation of large diagram, we have the frozen regions. They could be seen. They could be even seen here because just checking this example. But if we consider a larger example, please see that this picture of looks like that. I can kind of something. Yeah, okay, yeah, I have included this. Great. So yeah, so here there's a simulation, which and this is the last path here. It's actually it can be some curve, but well, that's another problem to describe limiting curve of such a thing. So actually we describe the shape of young diagrams, but actually that could be reformulated by describing the curve that would appear here in this the limit of the large relevance. Okay, can we go? So now, basically, there is just some technical words because we have understood that our dimension is the number of lozenges of trapezoid, and the number of lozenge tilings of the trapezoid could be reformulated as a number of configurations of n non-intersecting paths of length k. And just like the regular recipe I have shown, so just a little more note that we should make the paths longer, just to apply the LGB lemma. So LGB lemma allows us to calculate the number of paths with non-intersecting lattice paths between certain points using the determinant formula. This is a very well-known lemma, and if we put the starting points here, we can actually apply the LGB lemma and say that our dimension of lambda bar prime, which we have been looking from the very beginning, is actually equal to this determinant. And this determinant could be calculated. Okay, can I have the next? Yeah, here's a way to calculate the determinants, but I will be trying to solve this very profoundly right now. Is that okay? Like at this point, we have obtained the project formula. The project formula that I was talking about here, the same type of project formula now, and the same type of project formula like Kerf had when he had studied the asymptotics. Now this is actually doable, and you can get the multiplicity in this kind of expression. The important to know is that we have these CAIs, which are the positional points, but they are related to the row lengths of the Young diagonal. Okay, can I have one sentence? Yeah, so that is the summary of the combinatorial part. Is that actually we have obtained the multiplicity formula, which are factorizable for all the four series that I have been talking about. So the Skew Howe reality allows us to get the multiplicity for the VLN case in such an expression. This or what I have been explaining thoroughly. Then again, we will have the same type of formula for the SO12 plus 1. It's interesting that here we have a kind of determinant formula. Well, this is not a coincidence, actually. Later, I'll say a couple of words about this. We're also having such a formula for the multiplicity for SP2L modules. We also have this part looking like here, which also has this part with factorials, and then for the solve to M. So basically, that's the general combinatorial result that we have obtained from those reality that will later allow us to do some asymptotic calculation. But again, one must note that for DLN, EI is related to the rows of the diagram. And for other algebras, the relation with the row lengths is important. So again, one must know that for this series, the diagrams are, well, some of them have columns, some of them are just slightly modified. So because one must understand that the regular diagrams that we know are for GLN. So there are some around the bureau and other types of the bureau that we have used. Can we this? Yeah, maybe I can go. Well, I will just say a couple of words. So if we can formulate a certain problem using also the lozenges, but of course, actually, not actually, our result has been studied by from the board. So we can actually construct kind of like these tilings, but for other series. So we'll also have the lozenge tilings of the hexagon. The same problem remains, but it will be almost symmetric up to the middle. Also for SO12, we will have the symmetry for the blue tiles except for the blue part. But this is just the illustration. I won't be using that in my whole preparation. Yes. So now I don't have much time left, but I'll be talking really quickly about the asymptotical part. So again, just if the very problem in the statement of here, we can introduce the probability measure on Young diagrams for the GLN, GLN case. So consider just the example of GLN, GLN case with high value. So it's actually a uniform measure on matrices of zeros and one. Again, for the other pairs of Lie groups, we can consider the following measure. And so important thing that now we can try to derive the asymptotics. So, and for that, we use the explicit formulas for dimensions of lambda bar prime in terms of rho length lambda. So there was general result that we have dealt with previously to get those multiplicity formulas is how to plate dimensions of lambda bar prime with the rho length lambda. Okay, so so there are various ways to introduce some asymptotic analysis, as I have been talking previously, like in the symmetry case, there was a study of Petrov about the ensemble, like right here. We will have the Kravchuk polynomial ensemble. So how does it look like? So if you consider this measure, and you also put the dimension, you can finally see that here we have the determinant, and here we have the weight. And actually, this is the binomial coefficient, and this weight corresponds to polynomials. So that is a nice actual fact that well, allowed us actually to calculate also different asymptotics. But this is the approach of Borodin and Jokic. We in our first research we had different approach of shapes, but that is also one of the ways. So if we have the random matrix of zeros and ones, we can obtain two semi-standard Young developed shape lambda, then a random Young diagram, and then we say that okay, those Young diagrams, random Young diagrams, they correspond to the random configuration of points on the line. So here there is a line, and there is the points. So this is a determinantal point process, and now there is all the math that is related to the determinantal point processes that was well studied and could be applied in this case. So I'm not much happy to talk about this exact way, but maybe I will have time to yeah, I will just have time to state the theorem. So the theorem that we have proved for all Joe pairs that correspond to Skew Howe duality is the following. So if we consider the following asymptotics, well, n goes to infinity and k goes to infinity, and k over n goes to constant in the same limit, then if we have the upper boundary of the Young diagram, which is we can draw. So if we have an upper boundary of the Young diagram here, so we can consider this as a function of n. It will be rotated and scaled by 1 over n. So we scale by 1 over n this one diagram because we will consider the limit. Then, with respect to the measure that with the planetary measure that we have described previously, it converges in probability with respect to the supremum norm to some limit shape. Okay, so the limit shape actually. I don't have a picture here, but the way to describe this limit shape is somewhat not very direct. We can describe it using the density function, and the expression for the limit shape is like this. basically they're a little bit different for C greater than 1 and C less than 1. And can I have another one? Yeah, so okay. And here is actually the expression for the density. It could be a little simplified that it will be, but right now I have just this expression. So here you can see maybe this is a little bit, this example is a little bit small, but if we explicitly construct the function according to such a formula, we can see that here we have the sample here, and here we have this leading shape constructed by this formula. So for other dual pairs, we should have a slightly shifted argument. But here are the explicit examples for most probable diagrams, and you can see exactly maybe it's in the last page. Can I have the last one? So the last slide that I wanted to show you, maybe later you have some questions, I will say how to do that. So if we have this sampling of random diagrams, we can use the algorithms for dual scale for GLN, Euler insertion for SP2L, Bergen-Stromer, and other insertion for other series to obtain such a sampling. And here is an example of the random Young diagram, which is obtained by Euler's graph for GLPP and K equal to 150. So, and here is an example for a super. So, and it fits inside the larger picture. So, actually, it's not really reasonable to talk about this right now because I haven't told much about how the diagrams for this one look like and how are they constructed. But this is like context. So if we do the sampling, and here maybe it's a little bit small, so this picture is small, but you can also see the shape that is shown according to this formula we have related. So let me summarize for now the main results. So the main results is this limit shape theorem. We have obtained the limit shape according to such a formulas for this series of algebras, and for the statement of the this product decomposition of certain modules, which I have been said about previously. We have also found proof of the central limit theorem in the case. Using the fact with the polynomial ensembles, that's some special techniques. We have investigated the connection of this problem with the Schur polynomials and actually with free fermions. That's the course of Anton Nazarov, who is present here. So if you are interested, you can go to his course. He is explaining explicitly the techniques of how we use the free fermions in dealing with such problems. And also Pavel is also here. So Pavel Nikitin can also explain more about combinatorics. He has the course on symmetry groups, but actually it's already he had the last lecture.
Last lecture today.
Yes, he had the last lecture today. So next semester he will have lectures, but still you can come and ask him anytime. So these researchers are present here in BIMSA. So please contact them if you have questions and if you are interested in such a topic of exploring limit shapes and connecting such problems with prefermials, with also the representation of different position theoretic problems. So what do we plan to do? Well, in the next future, maybe we'll try to generalize this concept. Maybe we have to think what can happen in case of super algebras, if that is actually doable, because there is also the Skew Howe duality for these super algebras, which is studied, but we haven't reached the point of stating this problem for super algebras yet. So what I want to say is that that type of asymptotic representation theoretical techniques which started in St. Petersburg by Anatoly Moiseyevich Vershik, and we are representatives of his school, is continuing the study that he's also interested in. So this type of problems is also, they are also modern and actually also studied by the guys which shown by Warren, by Petrov, so in So if you are interested, you can contact any of us, and thank you again for listening to me, and I hope it has been understandable, and please ask your questions.
Are there any questions?
Too many questions.
Okay.
Very simple question, because I really don't understand in what kind of how duality we use. Because how duality general you take not just the product of vector or just rows, which is somewhere one version of overdimension correspondence. If you have product of columns, this is the so-called dual overdimension correspondence. So this is, as I understood, you just developed this approach for some ABC decrease. Decrease no. You don't know.
Decrease here.
Yes, the AX experiment.
Yes, okay, ABC. Okay. What I have to say. But one very important thing of representation correspondence and really how very that it really can be equipped with crystal structure. Yes, and this is very important because in something you have a scale, but what is it? Because there are a lot of insertions. Not only you didn't write that it is a scale insertion, that Robinson sheds include insertion. There are a lot of other insertions. Yes, and point what I want to say, I was asked, what happens if I take the product of rectangles? Not just columns, not just rows, but rectangles. In this case, we will obtain so-called little wood regions on Tableau and some bijection. Yes, what does it mean? You know, generalization of this construction, just not in the product of two representations, but in the product, in the power of product of seven representations.
Okay, what type of representation? So
In this case, it's the power and not important, but just general power between the product of arbitrary representations, and it is direct sum of something like right. Sorry.
And if you say that we have,
Sorry?
if you say that we have something like how duality in this case, so what is acting on the other side?
What is written here on the right hand side, but we will change what the first part is the dimension of reducible representation of GHN of some weight. Because this is depends really on the. Okay, it is a long story. Maybe we'll discuss.
Maybe let us discuss, yes.
Yeah, but and another for me important point. I don't really understand hypothesis related with asymptotics. Because how it's related, for example, we take a function. Because as I know, skew at a scale, really want to listen where you have skew. You mentioned skew power derivative, but skew at a scale here is combinatorial proof of skew power derivative. But what else? You mentioned many words combinatorial. Where is skew power here?
skew RSK and Olga mentioned dual RSK. So no skew tableau, just we get tableau.
No, it's true. No, it's difficult to explain. You need, okay. I understood that in your case, you have to consider the product of vertical.
Yes.
Mhm.
In this way, I think so called vertically strict tableau. So vertically strict tableau. And we have construct projection for vertically strict tableau. But in this case, RSK not enough.
Mhm.
Because RSK, okay, basically it is made for arbitrary positive matrices of slide. And by n, with some restriction on rows, yes. As I mentioned, do you have combinatorial proof identity analog of Cauchy identity for Taylor function? Because ordinary RSK is RSK gives you combinatorial proof of ordinary Cauchy identity. Now, it's a function that it's balancing the distribution of identities of double product of two Montgomery polynomials also takes nice form. But now you can specify limit for some Montgomery polynomials and degenerate it for Whittaker function. You are again obtain some nice combinatorial gain to Whittaker function, the Montgomery polynomials. With some relation, don't worry, it is also productive. And really, why it is important to consider as a product of forms? Because the character, well, you can define some statistics on the left and right hand side, and the RSK gives you combinatorial proof of identity for Whittaker function. And this is another important for sort of probabilistic interval system. And well, so for so long. Anyway, there are too many questions.
Okay, I'm very happy that today.
Yes, but it seems that the connection with the Whittaker functions is genius. So we should discuss the well modules on for the current vectors. So it's not that close to what's going here.
This is again some I don't know, misunderstanding, because Whittaker function really what there are two kinds of Whittaker functions.
Maybe you're speaking about the other.
Yeah. And in the realistic case, you obtain certain nonsense coefficient or decomposition of general Whittaker function on some basis. Yes. And
Well,
okay, then
yeah, I think that I would like to talk about this after the seminar, because it feels like maybe we have run out of time, but this is a very interesting idea. Thank you for such a question. I definitely need to think about this. Probably this connection is, well, for us still has to be more.
should be very fluent. Because
Yes.
very fluid for very quick so theory. Because in something that is too many questions.
Let's continue after the talk.
Thank you. Thank you.
Let's continue after the talk. Let's continue after the talk. After we finish with the talk.
Yeah, okay, actually, our co-author is spiritual. He obtained the formulas also for the q-deformations using the crystal-based approach. So we have also this part of our research. So yes, the answer to the first question is yes, the crystal techniques could be used in solving such problems. But as for Whittaker functions, I still have to think about it. We haven't used this approach. And well, I think this still has to be explored in the context of our problems. Thank you.
Thank you.
Other questions, comments? Okay, now let's start over again. Thank you.